Hey, AP physicists, I want to talk about the review for the test that's coming up. So this will be 1D and 2D kinematics, and it will include vectors. So just a real quick brief intro to vectors. Remember that if we're going to break our A and B up into components, we would break it up into an X and a Y component. Y sine because X is cosine. So you take the magnitude times the cosine of the angle gives you the X component. The magnitude times the sine of the angle gives you the Y component. And then we would do that in order to add and subtract our vectors. Look back over your notes on how we did those. When we get to the free response problems, there would be three different kinds of free response problems that you could see for this. The first one would be some sort of an equation. And whenever we're looking at an equation, you need to know your calculus. So remember that we're going to be talking about a position equation, a velocity equation, and an acceleration equation. And if we are going from position to velocity, velocity to acceleration, remember that we are taking a derivative. And vice versa, if we are going from acceleration back to velocity or back to position, then that's when we would be doing an integral. And so anytime you see an equation that is given to you, then that means you're going to be deriving or integrating. Graphs is the second type of question that you're going to see. You have to be able to quickly go from a position to a velocity graph to an acceleration graph or vice versa. So they'll give you one of those sets of graphs and you'll have to find values off of the graph and then find the others. And then a DC problem that you might have to plug and chug that might be a simple like two-dimensional constant acceleration where you're going to use one of the three kinematic equations that we used, the x equals VIT plus 1/2 AT squared, VF equals VI plus AT, or VF squared equals VI squared plus 2AX. And there are two sort of samples there. Look over the homework questions that you have and the worksheet questions, and then we will talk. I want to give you one of each of these examples further on in this video. So the first example, let's talk graphs. An object's motion follows the acceleration graph below. So you can see that this is an acceleration versus time graph. And we can tell because the flat lines that this is a constant acceleration, which means our velocities will either have diagonal lines or they'll have flat lines. At time 0, the object that is at a displacement of x equals 0. So it has an initial velocity of 5 meters per second. Part A, determine the velocity v at the end of each of the 5-second interval. Indicate your results by completing the following tables. So it's these guys down here. Show your work to the right of the graph. So if I look at this, then I want to find out the velocity. I'm going to label this as section 1, this is section 2, this is section 3, this is section 4. So in section 1, I know that my initial velocity is 0. I know that the time is going to be 5 seconds, and I'm looking for the final velocity. And I also know the acceleration based off of the graph there. So I can say VF equals VI plus AT. The initial velocity we set as 5. The acceleration is 0, and it's that for a time of 5 seconds, which means that the final velocity at the end of the first 5 seconds is going to be 5 meters per second. If I look at the end of the second 5 seconds, I can do the exact same thing. VF equals VI plus AT. So this is going to equal 5. Now I'm going to have an acceleration, though. That acceleration is going to be 10 times the 5 seconds that it's going to be at that. Oops, need a plus in there. So 5 times 10 plus 5 is going to be 55 meters per second. So this is going to be 55 for the second set of times. Now, if I look at the third set of times, my acceleration is back to 0. I can intuitively say, well, if I'm not accelerating, then my velocity has to stay constant at the 55, or I can do it mathematically. 55. 55 is my initial velocity. My acceleration is 0. And that's still going to give me 55 meters per second squared on all these squared. So this will also be 55. And then if I look in the fourth second, I can say the same thing, except I am decelerating in this case. I have a -5 for my acceleration. And I can say VF equals 55 plus a -5 times 5. And that's going to end up giving me an acceleration of 30 meters per second squared. So the answer to this is 30. Now, as I go to graph this, then I'm going to be looking at a combination of those numbers and the graph above, the acceleration graph. So when I look at the first part, I would say that the acceleration is 0, which means that the velocity has to be constant. So I'm going to take that velocity, and first thing I need to do is put marks on my on my y-axis here. So if 55 is my highest, then maybe I look at these and say 10, 20, 30, 40, 50, 60 looks like a good scale. So I'm going to say 20, 40, and 60 are the values for that. And whenever I look at the 5, then I'm going to say, hey, it's constant at 5. I'm going to do the best with a straight edge here that I can. And that's going to be the first part. Now, second part, if the acceleration is a non-zero flat line, remember that means my velocity will be a diagonal line. So I'm going to come all the way up to 55. And again, I'm going to try and use a straight edge here. And there we go. Not very straight, but better than if I freehanded it. And then the next one, again, I look at a zero line, which means it's got to be flat. So I'm going to have a flat line that stays at 55. And then the last one is the -5 acceleration. It's a non-zero acceleration. And because I have a negative value of the acceleration, remember this has to be a negative slope, or I come down from there to that final velocity of 30. So I'm going to come down to this 30 point here. Now, down in part B, we want to determine the displacement of the object above the starting point at the end of each of the 5-second intervals. So we're going to do something similar that we did up here with the velocity. We'll do 4 times in a row. Maybe we can use the x equals the initial position plus VIT plus 1/2 AT squared. Remember, sometimes we don't include this xi, the initial x, because usually we say we start at 0, but for each one of these different sections, we're going to have a different starting point. So at the beginning of the problem, remember that it told us that the initial position was 0, and so we can fill in just for that very beginning one. We can say that this initial position was 0. We know that the initial velocity at the beginning was 5. That was that way for the first 5 seconds, and that there was no acceleration at the end of that. So at the end of 5 seconds, we know that the object has traveled 25 meters. In the second one, now the initial position is going to be that 25. The initial velocity of the second one is still going to be that 5 times the 5 seconds that it's at that changing, plus the 1/2 of the acceleration, which was 10 in this case, times 5 squared. And whenever you throw that all in your calculator, you get 175 meters. So this first one is 25 meters. The second one is 175 meters. Now for the third one, we're going to do the same thing. Now our new position is 175. At 5 is the initial velocity. I'm sorry, for the third one, the initial velocity at the beginning is 55. And it's going to be that way for 5 seconds. There is no acceleration, so that part cancels out and goes away. And when we calculate that out, we get 450 meters. And then for part 4, last time, fourth verse, same as the first, we're going to take in and put our initial position in, 450. That's where we're at the beginning of this section up here. And then we come downward. So our initial velocity at the beginning of that section is 55. We're going to be changing it for 5 seconds plus half of the acceleration, which is -5 times 5 squared. And when you throw that into your calculator, you end up with 662.5 meters is our x value. So this guy is 450. This one is 662.5. So if I look at a scale for my graph, then I might say, let's see, 100, 200, 300, 400, 500, 600. Okay, so there we go. So this will be 100, 200, 300, 400, 500, and 600. So now I'm starting at an initial position of 0. If I have a flat acceleration and I have a flat but not 0 velocity, remember that my position graph is going to be a diagonal line. So I'm going to come up, if this is 50, I'm going to come up to the 25 mark, which is going to be that guy. And let's see if we do as best of a diagonal line as I can there. For the second section, then I'm looking at the end of that section being at 175, which is going to be right, oh, where did my line go? So I'm going to have a flat line that goes from here to there. Then 175. Now I want to look at that one and say, okay, well, if the acceleration is not 0 and the velocity is a diagonal line, then remember that the position has to be a curved line. And because the velocity has a diagonal positive slope, that means that I'm going to come into this and go into a concave upward curved line. For the next set of the lines, so remember I have a flat 0 acceleration. I have a flat but not 0 velocity. Again, that means that this is going to be a diagonal line. So I'm going to go from this 175 all the way up to 450, and that's going to be a diagonal line. And then lastly, again, I have a not 0 acceleration that's flat. I have a diagonal velocity, which means that my position graph has to be curved. And because the velocity graph is a negative slope, I'm going to curve concave down. So if I go up to 662.5, it's going to be somewhere in that point right there. And so I'm going to come up and sort of concave down for that position. And that's sort of a summary of what you might have to do whenever you're looking at graphs. So you would have to do some sort of calculation of the position, the velocity, and or the acceleration. And then you would also have to take one of the graphs and find the other two. So either you'll be given the acceleration graph, find the position and or find the velocity and the position, or you'll be given the velocity graph and you have to find the acceleration and find the position off of that graph. Another example, so we want to talk about the calculus that you would have to know in this first section for kinematics. Then you would be looking at the position, the velocity, and the acceleration. And one of the important things that you need to remember is that to go from your position graph to your velocity graph to your acceleration graph, that is going to be when you are taking derivatives. And if you're going the other way from acceleration to velocity to position, that's when you're going to be doing integrals. And so anytime that you see an equation, they're going to want you to demonstrate that you know how to take a derivative or how to do an integral. So a rock is dropped into a pond and sinks according to the following equation. So here's my pond, here's my rock right when it hits there, and then it's going to sink all the way to the bottom. And it follows this equation, y equals a negative 2t squared minus t plus 3. Determine the equation to describe the velocity of it. So if I'm given a position, remember if I have the velocity and I'm going to I have the position and I'm going to a velocity, then I'm going to be doing a derivative. So I'd take the velocity is going to be the derivative of the y with respect to t. You need to show this notation because that's one of the ways to show the reader that you know the calculus that goes with that. Now, to remember to take the derivative, we're going to multiply by the power. So I'm going to get a negative 4 in the front. I'm going to drop my power by 1, so it's going to become t to the 1. I'm going to multiply by the power, negative 1, drop my power to the 0, which means anything to the 0 is 1, so I just have a negative 1 there. And remember that the derivative of a constant is 3. So this is going to be our answer for the velocity equation. Next one, determine the equation to describe the acceleration. Again, remember to go from velocity to acceleration. We're going to take the derivative. And so I'm going to say the derivative of the velocity with respect to time is equal to my acceleration. And if I take the derivative of this with respect to time, I'm going to times it by 1, so negative 4, drop the power of the t to 0, and then the derivative of the constant is that. And so I'm going to end up with this. At this point, it doesn't say, but I'm going to assume that this is standard physics units. So this is going to be meters per second squared, and this is going to come out to be in meters per second, and this one is going to come out to be in meters. So how far will the rock sink? This is just looking at a concept idea here, and that is to, when I look at the position, remember that the constant at the end of the position really tells me what the initial position is. And I'm going to have to make this is a question I made up, so we're going to have to just assume that at this case, the rock is going to fall down. It's going to sink 3 meters because that's going to say it's 3 meters above the base of the pond there. What is the rock's velocity just before it hits the water? Again, it's the idea that the constant at the end of the velocity equation is really going to give us the initial velocity. So I can say that the velocity of the rock right before it hits the water is a negative 1 meters per second. It's a constant value. E, what is the rock's acceleration once it's in the water? Again, that's looking at this equation. In this particular case, we have a constant acceleration equation. If this were like negative 4t plus 3, then again, it would be the constant that's the end of this. Well, in this case, this is the constant, so we can just say that it's going to be negative 4 meters per second squared. Now, how long will the rock take to sink to the bottom of the pond? In that case, what we want to look at is we're going to say, well, if I know that the rock is going to go down a -3 meters, then I can look at this position equation, y equals a -2t squared minus t plus 3. I can put in the -3 is how far down the rock is going to go, minus 2t squared minus t plus 3. These essentially, if I take that to the other side, -2t squared minus t plus 6. Now I've got a quadratic that I'd have to solve. So either put that into your calculator in the quadratic or manually solve out the quadratic formula. And when you do that, you get a time of 1.5 seconds or a time of -2 seconds. So we automatically know it's not the -2. So it's going to take the rock 1.5 seconds in order to sink to the bottom of the pond. What is the rock's final velocity before hitting the bottom of the pond? Now we can take the velocity equation and plug that time in and say VF equals a -4 times 1.5 minus 1. And when you do that and solve, you get that it has a -7 meters per second. Now, again, remember that this isn't taking into account any friction that the water has. That will be a whole nother part of the problem that we'll add later in the year. And then lastly, how fast will the rock be moving after it has fallen half of the distance? So again, we're going to do more or less the same. I think I'm going to run out of space here, so I'm going to kind of commandeer this side of the screen. So if I do x equals, let's see, what was it? -2t squared, or the y value. Y equals a -2t squared minus t plus 3. If I want to know where it's gone half of that, then I'm going to have a -3/2. So it will have traveled half of that down, or -1.5. When I add that to the other side, I end up with an equation that is 0 equals -2t squared minus t plus 4.5. Again, I'm going to have to put that into a quadratic formula, and I end up with two different times. I end up with a time of 1.27 seconds, or I end up with a time of a -1.77 seconds. Again, it can't be the negative value, so I know that this is my time. Now, it wasn't asking for time, though. It was asking for velocity, so this is really asking for two different problems in one problem. And so I'm going to take that velocity equation again and say VF equals a -4 times the time, 1.27 minus 1, and solve for that. And then I'm going to end up with a -6.08 meters per second is how fast it'll be going only after half of the time. So that's an example of what some of the calculus might be that you'd have to do for kinematics. You would have a position, a velocity, or an acceleration graph. You would have to find, by integrating or deriving the other the equations, the other equations from that, and then potentially plug and solve certain numbers in to get those. Okay, final example. So we've talked about graphs so far. We've talked about the calculus that you would need to know so far. And the last one will be just a simple plug and chug problem. Now, granted, because we've only studied kinematics, you're probably not going to see a problem like this on the real AP test, because they're going to only have 3 free response questions that have to cover everything that we've covered all year. So they're going to integrate as many of the physics topics into one as they can. So even though I expanded this into a through H problem, you probably would only see the kinematics as like an A-B part, or maybe the GH part of a problem. But that being said, we're going to try and just do a basic kinematics problem. So a 15-kilogram cannonball is shot toward a castle wall that's 125 meters away from the cannon. So I know that the distance is 125 meters. The length of the cannon is 3.6 meters, and the cannonball takes 0.016 seconds to leave the cannon at a 5-degree angle. So when I read that, my initial thought is I really have two different problems going on here. I have the cannonball being launched in the cannon where its initial velocity is 0 till it gets to the end of the cannon. But then I also have the problem that's the 2D problem from once the cannonball leaves the cannon until the time that it hits the wall. So looking at the first part then, determine the magnitude and direction of the acceleration of the cannonball while in the cannon. Well, there you go. There's our 1D problem. So if I look at my cannon, so here's my cannon, and it's sitting on the thing here. I have a cannonball that's in here, and it's being launched this way. Well, a couple givens that I know the initial velocity is 0. I know that this length that the cannonball is going to travel down is going to be that 3.6 meters. And I know the time that it takes to go that distance is 0.016 seconds. So when I look at those three givens, if I'm looking for the acceleration, then I have to pick one of the three constant acceleration kinematic equations that we have. And since I don't have final velocity, it means I'm probably going to use the position one. So x equals VIT plus 1/2 AT squared. I have 3.6 for my position. My initial velocity was 0, so that term cancels out. Half of the acceleration times the time, 0.016 squared. Now, if I calculate all of that, so take the 0.016 squared, divide it by 2, divide that into the 3.6, I end up with an acceleration of 28,125 meters per second. Now, one of the most common mistakes that I see from my students is that they did not answer the question correctly on this if they leave it at that, because the problem doesn't ask for just the magnitude of the acceleration, it also asks for the direction. So you would lose a point, or depending on what the point system of the problem is, several points based on that. So I would say 28,125 meters per second. And remember that it's going to accelerate at the same direction that the cannon is at. So this would be at 5 degrees because it can only accelerate in the same direction as the force that's acting on it. So what is the velocity of the cannonball as it leaves the cannon? So now we're looking for that final velocity. We can use either one of the other two equations, the kinematic equations. My preference would probably not to be to use the square one. So VF equals VI plus AT. I'm looking for that final velocity. The initial velocity was 0. The acceleration is the 28,125, and it accelerates for that 0.016 seconds. So the final velocity as the cannonball leaves the cannon is going to be 450 meters per second. Next, how long is the cannonball in the air? So now we have to look at the part where, okay, so here's the cannonball, it's launched this way, and it's going to potentially hit a wall that's over here. We know that that wall is an X distance away of 125 meters. We also know what the initial velocity when it was fired from. So I'm going to look at potentially using the X equation to solve for it, or I'm going to look at potentially using the Y equation. Now, I don't know exactly if it hits the wall or not. So the Y equation is sort of a gamble because I don't know that it hits the wall at 12 meters. But I do know that the wall is 125 meters away, so I can do X equals V cosine theta, which is the initial velocity in the X direction, times the time. So 125 is equal to the velocity, 450, times the cosine of 5 times t. And when I solve for t, that is going to give me a time of 0.279 seconds. That's how long the cannonball is in the air. Now, part D then asks, does the ball hit the castle? So this is where we're going to look at the y value. And now that we have the time that it is in the air, we can use the y equation, y equals v sine theta, which remember is the initial y velocity, times t plus 1/2 at squared. So the y value is what we're looking for. The initial velocity was the 450, the sine of 5 degrees, times the time that we know it's in the air, 0.279, minus 4.9 times 0.279 squared. And when you solve all of that, you end up getting a y height of 10.6 meters, which tells you that, yes, it actually hits the wall. And if the wall was, what did it say at the top of the problem? If the wall is 12 meters high, then we know that it hits at 1.4 meters below the top. So all of that sort of is combined into the answer. If so, how far below the wall does it hit? That's what it is. It doesn't hit above the wall. Now going back up to E, when the cannon is actually shot, does the ball hit at your answer to D? And so I would look at this and say, no, it's not going to hit because there are several different things that happen. Remember that we consider this free fall where the only thing acting on it is the acceleration of gravity. However, there is another force acting on it, and that force is going to be friction. So we can say no, and the reason would be because of air friction. But then there's also another friction that we didn't take into account. That would be the friction that the cannonball has inside the cannon. So it would also be because of the surface friction in the cannon. So both of those would be reasons why it would not hit at that part. So it would actually go just a little bit less than what it was projected to be because of the friction acting against it. So explain one method that you could use to get the cannon to shoot farther. The most obvious method would be to use more gunpowder, right? More gunpowder. But that's not really what they're looking for here. They would be looking for something that is physics related, although yes, that does add more force to it. What we're going to do though is we're going to say something like maybe we would shoot this at a 45-degree angle. Because if we shoot at a 45, then it has the maximum distance. It balances that height and the X position. Determine the maximum height of the cannonball. So we want to look at, if we're talking this point right at the peak, at the very top of that. And remember what we know at the top of the parabola is we know that the final velocity is 0. So if we're looking for the position at that point, the maximum height, then we can do VF squared equals VI squared plus 2AX, or in this particular case, because we're dealing with up and down, we're going to say 2AY. The final velocity at the peak is 0. The initial velocity is that 450 times the sine of 5. Don't forget to square it, plus 2 times a negative 9.8, which ends up being negative 19.6, and times the y displacement. So do this term, take it to the other side, divide it by the 19.6 with the negative, and you end up with a y value of 78.5 meters per second. And so that's how high the cannonball is going to go. Now, last question is another concept question. We run out of 15 kilogram cannonballs and we use an 8 kilogram one instead. So assuming that the 8 kilogram one leaves the cannon at the same initial velocity, then how will this affect where the cannonball hits the castle? Again, this is just a concept, and it's asking you to say, well, does mass really make a difference with kinematics? And the answer is that it does not change it. It does not change. Because for several different reasons, you could say mass doesn't make a difference. Mass doesn't make a difference. And you could also say, you could justify that by saying, well, whenever I look in the kinematic equations, there is no mass in any of these equations, no mass in the equations. And we'll talk later whenever we get into dynamics or forces, why that is, because typically the mass that is in the equation, it cancels out. And that's why we end up with these kinematic equations that have no mass in them. So again, this would be a really, really basic, something you probably would not see all of this on as an AP test question. But since this is all we've covered, I've expanded it out just to give you different concepts that they might throw in to any of the different problems. And so just in summary, we have 3 different parts that you want to know. You want to know the graphs, how to go from a position, velocity, and acceleration graph and do some of the calculations. You want to know how to do the calculus that goes with some of those, where you'll be, if you're given an equation, you know automatically you have to integrate or derive that equation to find the other equations, position, velocity, and acceleration. And then lastly would be a basic 2-dimensional constant acceleration problem.